college class today, but that's okay. We're good with that. So for our agenda, you should have your agenda, and we're going to be looking at, we have a warm-up task, which is actually on the reverse side of your agenda. So just sort of saving paper there, so we'll work on that in a couple minutes. And then the chapter from Vanderwall for today was chapter 13, where we're looking at algebraic thinking, generalizations, patterns, and functions. And then we're going to tie that back in with the NCTM Effective Math Teaching Practices. So do you remember the first day of class when we didn't all have our books yet, and we started out with these 8 effective math teaching practices? And then that ended up being in chapter 1, and hopefully we've embedded that throughout the semester. So we're going to go back and use the hexagon task to look at the effective math teaching practices as we look at a class work through the task that we worked through in the beginning. And then we'll have wrap-ups and reminders. We'll talk a little bit more about final exam expectations, and that'll be our class for today. So our topics are algebraic thinking, generalizations, patterns, and functions, and then going back and looking at those 8 effective math teaching practices. All right, so to get us started, I'm going to give you some time to work on the hexagon task. So for this task, I've put the tables, these yellow hexagons that we used when we were talking about fractions the last couple weeks, but we're not going to talk about fractions today. So when we put these together, we're going to call them trains. So you'll see trains 1, 2, 3, and 4 on your paper. And these are the first 4 trains in the hexagon pattern. So this is our first train. And when we place 2 of the sides adjacent to one another, that's our second train, and so on. So for each subsequent train, we're adding 1 additional yellow hexagon. So for the hexagon pattern task, you're supposed to do these things. Compute the perimeter for the first 4 trains. So what do we mean by perimeter? Yeah, the distance around. So what unit should we use to measure if this is our hexagon?
Inches.
Okay, so we could use inches. What if we don't have a ruler? And I'm just letting you use the things in your box today.
Use cubes.
You could use cubes.
You can use the hexagons.
We could use the hexagon. So since all the side lengths are the same, and we've looked at the relationships among the pattern blocks, notice how the side length of the hexagon is the same as the length. So this will be 1 unit. So we'll just use a unit, and we'll define that as one of these side lengths. All right, so you're going to compute the perimeter for the first 4 trains, determine the perimeter for the 10th train. But I didn't give you 10 hexagons, so you're determining it without constructing it. And then write a description that could be used to compute the perimeter of any train, and be sure that you can explain it.
Formula.
All right, yeah, the formula or the generalization. So, excuse me, take about 10 minutes, and I'll set a timer just so we don't get too far off track. You can feel free to talk to one another about it, but we'll work on this task, and then at the end of the 10 minutes, we'll set it aside, and then we're going to come back when we look at a video of Ms. Rawson's class as they work on the task. Sound like a good plan?
Yes.
Okay. Let me set my timer. Excited to see what y'all come up with.
I'm excited too, Dr. Ivy.
I'm so glad.
Sarah, do you want to work on this together? Yeah. Okay, good. Okay.
So you have about 1 more minute.
Okay. Okay. Now
Statements.
we can say each train has 4 more sides than the preceding train, because that's actually
Yes.
true.
Each train.
Oh gosh, 110?
I can solve that.
We need a formula.
No.
So what is number 5 asking?
Determine which train has a perimeter of 110. So like, you're just determining whether like train 4, you know, like you're figuring out which number train. And we know it has to be bigger than 10.
I know what you do, maybe.
uh,
So we know that train 5 has 22 units. So what is? Oh, time's up.
You can finish your thought.
I was gonna say, we know that train 5 has 22 units. So what if we just like did 110 divided by 5 and then multiply that by the. Are you following me? Dr. Rose, are you following
I
me?
hear what you're saying.
I'm following you up until the point of where you said then add it. I understand why you want to divide 110
Because
by.
we know that the 5th train has 22 sides, so we can see how many 5th trains fit into 110, and then we have to multiply that by 22 sides since each train has 10 each.
Oh, I see what you're saying now.
Do you really, or are you
Yes.
just saying that?
No, I do see what you're saying because in train 5 there are 22 sides
Yes.
or 22 units. So then what's 110 divided by 5?
22! Whoa, wait. 22. And then we know that each 5th train has 22 units, so we would multiply that by 22. And 22 times 22 is 484. So the 484th train has, wait, the 484th train has 110.
That's
Is
not
that
right.
right?
No, that's not
right. Oh, I don't
So
know.
I want us to leave that because what we're gonna do is circle back to this problem,
Okay.
okay? But I did write down your starting point for your
Sorry.
explanation, like Sierra said, correct me if I'm wrong, you started with train 5 perimeter is 22 units.
Yes.
So if we need to know which train has a perimeter of 110 units,
Yes.
then,
Divided by 22.
is that what you were saying? And so I have 2 questions. One, is that what Sierra's saying? And 2 is, would that work?
Well,
So, go ahead.
I said, since we know train 5 has 22 units, we could divide 110 by 5, which would break that 110 into trains of 5. And then, but maybe Star's right by dividing it by.
No, because then you get 5. Because 5 times 22 is
I
110.
think we're getting at something, but I don't know what we're getting
Yes,
at.
we're getting something, but we don't know what we're getting at.
So I want to leave us in disequilibrium.
Oh,
okay?
good.
Okay.
Thank you, Dr. Ivy.
We are going to come back to this,
Okay.
but for right now, I think you've gained familiarity with the problem. You've worked through parts 1, 2, 3, but you're still working on that 4th extension. So I'd like to come back to that when we peek in the classroom. Are you guys okay with that?
Yes.
Sure.
Okay. We do need to come back to it, so I wrote it on the board though. Okay.
Do you hear that sound? Like, is somebody singing?
I do hear somebody in there.
They heard us say that. I'm sorry, whoever's singing. Is it
You're welcome
Kenna?
to come join us.
Is it Kenna?
Are you singing? Okay. Would you like to come to class again?
She's recording. Dr. Cahill's watching us.
Hi.
It's Kenna.
Oh my gosh, what a big class you have. We do our best. All right, so we're gonna flip to chapter 13. I'm sorry?
I was just saying all right.
All right, so that was our focus for this week. So in chapter 13, our learner outcomes include that we want to be able to describe ways that we can build on number sense. We've been looking at things like fact fluency, basic fact fluency for students, addition and subtraction algorithms. How can we build on those to help students to gain a great foundation for algebraic thinking? And then second, think about how patterns and functions fit in with the idea of building algebraic thinking. Thirdly, identifying strategies that we can use to teach about equivalence. So we're going to look specifically at one topic related to that. very strongly. And then finally, how we can use mathematical modeling throughout this process. So it's all about algebraic thinking, generalizations, patterns, functions. You got something?
I was thinking about the train problem. I'm sorry.
No, that's okay.
I'm gonna think about it.
Do we need to write something else over here so we don't lose it?
No.
You sure?
Yes.
Do you need to share a revelation?
I don't remember what it was now, so.
Oh, okay. All right, so as we usually do, I want us to think about standards-based development. So I know that you will be a teacher assigned to a very specific grade level, whether you're kindergarten, 3rd grade, 4th grade, and you're gonna be thinking about the requirements at that level. But we also realize that mathematical concepts are built over time. So I want us to look briefly at our progressions. So in kindergarten, students are learning about addition and subtraction, but primarily with objects, with fingers. They're learning to associate, as they count one item, that idea that one of those items corresponds to one number when we're counting, and that there's a symbol that represents that total quantity. They're acting out situations, and they're just starting to get into formalizing what's a number sentence, what are the symbols associated with that.
Dr. Ivy,
Yes?
my students this week, they just started addition this week. And when I was there, I was there 2 days this week because I had to make up some missed field hours. And on Tuesday we did this game, and they got with a partner and they had like an addition like map in front of them. And what they did was they rolled a dice, and then whatever number came up on the dice, they had to count that many like counters out and put them in the first box. And then they rolled a dice again, and then they put that number of counters in the second box. And then they had to write addition sentence that went with the blocks up at the top. So like if they had 5 blocks, they had to write 5 plus 3, and then they could count the blocks to see what the answer was.
Did the dice have numbers on them or dots? They still had dots. That's interesting.
And like my students did really, really, really good with them. Like I was kind of expecting them not to like do super great because it's like kind of like a hard skill at first, but they did awesome with it. I was walking around and like watching, you know, I really wasn't like helping, I was just kind of watching, and they did really good with it. Yeah, I was really proud of them.
Yeah. So, and you're in kindergarten class?
I'm in kindergarten, yes.
Okay. So, yeah, that's a great connection to this idea that they're doing that, right? They're learning to count, they're learning about numeracy, they're learning about units and how they can, one object corresponds to one more as they're counting. But that number aligns with the quantity of the entire group. And then your elementary kids, they are starting to think more about patterns. Oh, kindergarten kids are also thinking about patterns. Your kids have probably done some of this, thinking about repeating patterns. A, B, A, B. Blue, red, blue, red, blue, red, what's the next color, right? And as they master that, they start to think about A, B, C patterns. And they do repeating patterns way before growing patterns. But elementary kids are starting to think about algebraic ideas as they start to connect algebra especially with the properties of operations. So we looked at associative and commutative properties of addition and subtraction, for example. Those are ideas that carry on as they learn algebra formally. And then middle school students, they start to really study algebra in more abstract and symbolic ways. Focusing on the understanding, they start to learn about variables, and they build on these numerical expressions and equations from elementary school to write algebraic expressions and equations, so they may have variables in them. And then in grade 8, they start to think about functions. So it all works together. Even if you think about yourself as an elementary teacher, you're still an algebra teacher because you're still laying that foundation. And if you look in the standards, you'll see the algebra conceptual category is present for all of your elementary kids. Sierra.
I was going to say something about the praxis. So when taking it, I just realized that you can use algebra for almost everything on that test. And if you know how to use it wisely within each problem, it really helps you. And it just made me realize that algebra is really interconnected with everything. And it was kind of weird, noticing that. Because, usually you think of algebra as find X or do this, but it's literally in almost everything, and it's so weird.
Isn't it awesome?
It is, it really is.
Like when I was I was one of the kids that would always be like, when am I gonna use this?
Yeah.
But now that like I've gotten older, I'm like, wow, I actually am using
Yeah,
this.
it's so
Yeah.
good. And it's more of a tool that you
Mhm.
can use rather than like, I don't even know, but I feel like it's a great tool to have if you actually know how to use algebra.
Oh, that's
So-
such a great disposition to have too, like to
Yeah.
feel like you have that tool in your toolbox that you can pull out in a variety of situations beyond an
Yeah.
algebra classroom. So, thank you. So when we think about algebraic thinking, and again, we're thinking beyond middle school where we still start to see algebra formalized, we're thinking down into elementary school. We see three strands of algebraic thinking. So first of all, the study of structures in the number system. The structure of the number system extends to algebra. So those are skills that they will use. Secondly, the study of patterns, relations, and functions. So those patternings that students do, eventually they can use variables to correspond to those patterns. And then finally, the process of mathematical modeling, including the use of mathematical symbols. So we're going to look at a few of these things just to give some exemplars. Again, these are just highlights from chapter 13 before we jump back in and look at the hexagon task. So they're all in your book as well. So for connecting numbers and algebra, so number operations with algebra, sort of the idea of connecting fact fluency, operations with numbers, with algebraic reasoning. So first of all, let's look at number combinations. So here's an example. 7 birds have landed in your backyard. Some landed on a tree and some are at your feeder. How many birds might be in the tree and how many at the feeder?
You want us to solve it?
Yeah, I want you to kind of talk to me about this and why might this
So-
connect numbers and algebra.
You know that there are 7 birds, and you can really see how many combinations you can make of birds on a feeder and then birds in the tree.
3 and 4, 5 and 2, 1 and
Yeah.
6.
All
Yeah.
those combinations, so there are multiple possibilities and multiple answers.
Absolutely. So then you could generalize about them. So if you had a variable that represented the number on the tree and the number on the feeder, so T and F, for example, what would you know about the relationship between T and F?
It equals 7.
The sum, right, the sum must be 7. So now you're connecting algebra. Certainly you could do this without any formal algebra skills,
Yeah.
but those generalizations, those things you say about there could be many combinations and in each combination they sum to 7, that's algebra. That's algebra for elementary kids. So that's your job, is to foster that early algebra in elementary school. Place value relationships. So the sum of 49 and 18 can be found with the use of a hundreds chart. So moves on the chart can be recorded with arrows for up and down. So in that way, you're using the structure of numbers as you think about the hundreds chart to add up and down, and then to go over for your ones. And then finally, algorithms. So shifts in how arithmetic problems are presented can open up opportunities for generalizations. So oftentimes we'll give kids a set of similar problems so students can look at the structure and describe the patterns they see. So what do you notice here with this set of, so these are equations, but this should be a blank or a box here. It's just not showing up. So 1/2 times 12, 1/4 times 12, 1/8 times 12, 3/4 times 12, and 3/8 times 12. Why might you pose that to kids?
Thank you for
It's really
yeah.
distracting.
Thank you for doing that. I don't understand really like what.
So like all of those fractions are. You say
they're all 2, 4, and 8 are all like multiples.
So
of
those are all like, those are all parts, like, you could break 1/2 into 1/4 and 1/4 and 1/8, and then,
Yeah,
I don't know.
So these are fractions. I'm sorry, Sierra. You asked me before class if we were talking about fractions. We're talking about algebra, but in this case, we have to do some fractions. Okay. So yeah. So these are So the first three are just some unit fractions, right? They're all have denominators that are powers of 2.
Yep.
Okay, so what do students usually think when you multiply a number times another number in terms of, will the number get bigger or smaller? Okay, so bigger. So students typically think the number will get bigger.
Those get smaller though.
These get smaller.
Yeah.
So that might be one pattern students recognize. Another pattern might be the relationship between these different products. So this patterns with numbers, we need to think about that. If, for example, I knew that some number multiplied times 12 gave me 6, what would I be able to discern about that factor that I multiplied by 12? If it got smaller, if the product was smaller. You want me to restate the problem, the
Yes.
question I'm asking? Okay, so typically students think that when we multiply two numbers together, the results will be larger than
Yes.
either of the numbers. So that's a common thing based on what they've experienced so far.
Yes.
But we said what happens here is that they get smaller. So let's say I had said blank times 12 is equal to 6. What would you know about what was in the blank? What was covered up?
Blank times 12 equals 6, you would have to know that it's a really small number because
Yeah.
if you do like 12 times 12 or 12 times 2 or
Yeah,
even 12 times 1.
it'd have to be something less than 1.
Yeah.
It's got to be something less than 1. So a
Yeah.
fraction, decimal, some number less than 1. So, for example, if I had given a group of students these first 3 problems, it might be that I wanted you to discern a structure about mathematics. Sometimes we multiply two numbers and the result's not bigger than both of the factors. It's smaller. And when is that the case? It's when the number might be less than 1. For example, one of those factors, at least one of the factors might be less than 1. So some of those rules that they may have learned that you want to go back and help them make some generalizations about. So this all connects to algebra. All these tools in your toolbox, you've got to make sure those tools are real tools that last and not rules that expire. Isn't this exciting?
So exciting, Dr. Ivy.
I'm excited. All right, so going back to this idea of structure in the number system, I wanted to bring in this table. This table is in your book. So why did I bring this table up to talk about as we review chapter 13?
Well, because a lot of algebra
Yeah.
problems follow these structures.
Yeah. Just a number of groupings.
Yes.
Mhm.
Do you want to say more, Sierra?
Just the way that problems can be structured and the way numbers are grouped within those structures.
Can determine your answer, like.
Yeah, and you solve each of these different ways.
Absolutely. Up to this point, you've seen that your students, your children, have seen these with numbers, okay? With numbers. But they're going to use this tool, this idea of the associative property or the identity properties, for example. They're going to use those tools even when they don't know what numbers go there. Even when it's a generalized for a variable. It's still going to work.
Numbers and numbers.
You'll have some variables. And remember last week we looked at the misconception, one of the examples in the error analysis. Star, you haven't done this yet, I know, but where had to do with the additive identity, and the student whose misconception was that if you subtract 0, you get the answer of 0, because they were confused with what happens when you multiply times 0, so they were overgeneralizing this rule that they learned. So precision and experience with all of these properties matters for addition and subtraction in your operations. It also matters when you continue and expand that into algebraic thinking. You guys are laying some really important foundations. It's exciting. All right. Pattern. So also another piece, another one of those strands had to do with the study of patterns and functions. So what's happening over here on the left side?
It's like yeah, it's just patterns.
Patterns.
Yeah.
What kind of patterns?
A, B,
Yeah.
A, B, C, D.
Yeah, A, B, or A, B, 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 A, B, 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 A, B, B, B. These are just repeating patterns.
Yeah.
And your kindergartners, they need practice with repeating patterns. When you see repeating patterns as one of your standards, it may not be super clear at that moment where it fits in, but this is important. Patterns are that simplest form of algebra that students are experiencing in school. So they're building on those patterns. What's happening here with the pattern blocks?
It's a growing pattern.
Exactly, a growing pattern. So we had our repeating patterns over here, growing patterns
Is
over
that
there.
kind of like that block, you know, we did in like one of the first classes where we like added blocks and then you like had to decide like what would the 50th one look like or whatever?
Absolutely. So was that the staircase task?
Yes.
So the staircase task, yeah, that was a growing pattern as well. So it wasn't the case that we were adding the same number of blocks each time, or that we were repeating anything that was growing. All right.
Oh, I'm sorry, that did like not register in my brain what that was on the screen. I thought you had something covered, like, you know, like, you know, you can like hide things. I thought you had something covered, and I was like,
Like I just covered all that blank space
I was
over
like-
here.
I was like, why is it so small that she has covered? I didn't realize that was it.
Yeah, it's
I'm glad Dr. Cahill heard me say that.
That's okay. That's okay. It's an equal sign. So what is an equal? We're talking about algebra. We're talking about things that we need to use, which is pretty much everything from elementary school as we move to middle school, and we're thinking specifically about algebra. Why did I put an equal sign?
Because after you solve the problem, you know what it equals.
Yeah, like kind of like, well, it's kind of like what you just kind of said with the fractions a little bit. Like, if you don't know one of the, like if it's like a plus 5 equals 7 or whatever, well then you know that whatever you put for a, it has to equal 7.
Okay.
Are you ready?
Yeah.
So,
You could have thoughts even without the camera.
the equal sign, I feel like a lot of kids just see it as like, oh, I solved the problem, so I know what it equals, but you also have to remember that it represents that both sides of the problem are the same.
Yes.
Yeah. So I feel like a lot of people never stop and think about that, like what that sign actually means.
That's what I was trying to say, but I didn't
Yeah.
say it in those words, but that's what I was
Yeah.
trying to say.
Can you re-say it now that you've heard
Yes.
Sierra say it?
So, like, because in algebra you use variables, so letters a lot of times. And so if you have like something on the right side of an equation, you know that the left side has to be like 7 if this side is 7.
Right.
So it has to be the same on the left side as it is on the right side.
Yes. So this is a huge idea. I'm just making sure we can see you. Sorry.
Dang, I said something good thing, I wish I was in the camera now.
Okay, so, yes, so you guys are exactly at the right spot. So what's important here to think about is the two different ways that students can envision this equal sign. So as you guys have said, like Sierra said, it's got to mean this balance. Everything on the right-hand side represents the same quantity as everything on the left-hand side. But instead, what happens?
Some kids just,
Kids don't understand that
yeah,
concept.
they just see it as like the answer to the problem.
Yeah, so students have a visual. They get calculators that look like this.
Yeah.
And what happens with a calculator that looks like this?
You just put your numbers in, press equal, and it gives you the answer.
So what is the button with the equal button, with the equal sign on it do?
Just gives you the answer.
It computes the answer.
Yeah. It doesn't
And so
even show
students
you.
get confused. If you get a calculator like this, scratch it off. Scratch the equal sign off or put tape over it or something. It's so confusing to kids, it sends the wrong message.
Yeah. I feel like that is the reason why a lot of kids just see it as the answer button.
The answer button.
Let's just call it the answer button.
You good?
But what about the
No.
Texas Instrument calculators that literally show you all of the steps you took to get to the answer?
So Texas Instrument calculators will show you, will actually say enter on them.
Yeah.
Yeah.
Oh, they say enter. I never thought about that.
So I'm just a little confused. Why don't you like that they have equal signs on them?
Because it's the answer button.
Because the kids will become accustomed to 6 plus 3 equals 5 minus 2 equals. And so what we're doing is we're teaching the kids, or the kids are learning, that the equal button means to do whatever operation preceded it. So then they get a problem that says 7 minus 8 equals B minus 6. Okay? Or even box. Let's go earlier, before we have variables, oftentimes kiddos will see boxes here.
Yes.
But if they think this means to do whatever operation preceded it, what are they going to put in the box? Well, let's do 9 minus 8.
They're going to put 1.
They're going to put 1. 9 minus 8 equals box minus
Okay.
6.
Not equal 1 minus 6.
Yes, I've seen lots of kids do that.
So
It's-
that's why the button is like just saying like, oh, this means the answer. So they just put what they think it is rather than actually seeing that
That they have
equations
to equal each
balance.
other.
Yes.
Okay, I get what you're saying now.
So when we start to look at what this means, or how we can say this mathematically, students are developing an operational view of the equal sign. So what are our mathematical operations primarily in elementary school? What are the operations?
Addition, subtraction,
Multiplication,
then we get to
division.
division, multiplication, and that's really where we stop.
Yeah, addition, subtraction, multiplication, division are the most common operations we talk about for elementary kiddos. The equal sign's not another operation,
Yeah, it's not simple.
but that's the view that we're describing here as students develop that misconception. So instead, we want to encourage a relational view. So the equal sign tells us about the relationship between the numbers on the right-hand side and the left-hand side. So operational versus relational. And one of the ways we see curricula address this is by changing where the unknown lies. So if you're doing addition problems, your kindergartners are doing addition problems, many of our curricula now will say blank equals 4 minus, or let's do addition, 4 plus 1. You notice it doesn't always go in the same direction.
Yes.
Okay, or it might say 5 equals blank plus 1. The students are developing some flexibility with addition. They're also developing a more relational view of the equal sign that will carry them. Isn't that exciting to know though?
this. Yes.
You like this?
I like it, yes.
What do you like about it?
I just like that we're like making more meaning with the equal sign rather than just using it as the answer button.
Yes.
Yeah, I don't know. I feel like it's important for kids to realize this before they actually get into doing like all those like harder concepts.
Absolutely.
Because once you get up there, the equal sign isn't just the answer button. It's
Yeah.
way more, so.
But depending upon the problem types in your classroom and the curricular you're using, sometimes the operational view gets them through
Yeah.
for a period of time. And then when they start to see problems that are moving toward more of an algebraic feel as they formalize algebra, they run into this big roadblock because what they thought the equal sign was, it isn't anymore. So if you can keep that in mind, even before it's a necessity, you're not teaching something that has to be retaught differently later. I like it too. Oh, fun. Okay. So the big idea here, before we bounce back and look at the hexagon problem again, is that your foundations for algebraic thinking begin when?
Kindergarten.
In kindergarten. So forms of algebraic thinking, those strands we talked about, include thinking about and analyzing the structure in our number system, studying patterns, and studying relations and functions. And of course, within the structure, we appreciate this idea of developing a relational view of the equal sign. So you guys are algebra teachers.
Yay.
Wow.
Never knew I'd be an algebra teacher.
So regardless of which grade you teach, if someone says, what do you do? And you want to, you can just say, I teach algebra. Also teach geometry and statistics and teach lots of stuff. Yeah, claim it. All right, remember our first day of class?
Yes. So long ago.
And Star was talking about our task from that day, our staircase task. We also brought out these 8 effective mathematics teaching practices. Do you guys remember this list? So you have in your folders, this handout, so I gave you another copy in case you don't have the one from day one handy.
I still have it.
You still have it? So, I'd like you to take it out and take just a few minutes to read over it because we're gonna watch a classroom in a few minutes, and I'm gonna have you note how the teacher engaged in these. So you're gonna go through the transcripts,
It's
after
kind of like
watching
the
it.
Hungry Caterpillar that we did.
Yes, it's like we did with the Hungry Caterpillar, or we're gonna do with Text Line Class. All right, so I'll give you a few minutes just to read on that.